Alright, now that we have the idea of a basis as a set of linearly independent vectors whose span creates the vector space, I think it's more helpful just to work through some of the even problems from the homework rather than talking more theory. So let's take a look at some of the even problems. Just wanted to start with like 2, 4, 6, and 8 here. Here they're specifically, rather than talking about a span, they're talking about a known vector space, R3 in this case. So they're just saying which of the sets from 1 through 8 are bases. The plural of basis, by the way, is bases, just with an E instead of an I, for R3. And again, this is a reminder that a basis isn't unique. There can be more than one basis for R3. So maybe several of these will be. We'll find out. Okay. Which ones are basis for R3? If they're not, find out which ones are at least linearly independent sets and which ones span R3 even if they're not a basis. Okay, so let's work through these. Let's start with number 2. Generally, it's going to take 3 vectors to span all of R3 space. They need to be linearly independent, though. I can already see the 0, 0, 0 vector is one that we know is not linearly independent by definition. It is a combination of the other two. I could take 0 of the first one plus 0 of the third one and create the second one. So this is, number 2 is not a basis, first of all. So not a basis. Also not linearly independent. That's why these 3 are not a basis. Not linearly independent and doesn't span R3. Let's take a look at number 4. 4 is also three-dimensional vectors. And there's not an obvious linear dependence here. Maybe there is, I just can't see it right away, unlike the 0, 0, 0. So probably the easiest way to check on number 4 is just going to be to row reduce and see if I've got 3 pivots or not. So go ahead and grab your favorite row reducing tool and dump those in. And after row reducing, we can see that, yeah, it's equivalent to the identity matrix. There's 3 pivots, so therefore the columns are linearly independent, so therefore it is a basis. So yeah, this is a basis for R3. 6, I can already tell, is not going to be a basis for R3. There's not enough vectors. There's only 2. So it's not a basis, so now we need to see if it's, at least if the set's linearly independent. Since there's only 2 vectors, the only thing we need to check for is one a multiple of the other one, and I think it's pretty easy to verify that that's not true. So these 2 are linearly independent. If you really wanted to, you could stick them into a row reducing tool as one matrix and see that there's going to be 2 pivots. But anyway, not a basis, but it is linearly independent set. I totally spelled that wrong. and does not span R3. Okay, let's look at this last set. It is 4 vectors in R3. I already know when I row reduce, at most I could have 3 pivots here. So I already know that this is maybe too big of a set. It is too big of a set, so it's not a basis. These are not going to all be linearly independent. Not a basis. And so therefore I already know not linearly independent. This set might span R3 though. I've got 4 vectors here, so it's possible by combining all 4 of these vectors that I can get everywhere in 3-dimensional space. You know, I might just have too many vectors to be a minimal spanning set. But I need to know still that there's at least 3 linearly independent columns here. There's at least 3 pivots. So at this point I need to grab my calculator again and check for 3 pivots. So there we've got row reduce. And there are indeed 3 pivots in the first column, the second column, and the fourth column. So it does span R3. And they didn't ask for it here, but it would be the first column, the second column, and the fourth column that would be necessary to span R3. It's that third column that happens to be linearly dependent. All right, let's move on to some further examples. So for 9 and 10, and we'll look at 10, find a basis for the null space. And they refer you back to an example. But really what we need to do is first of all describe the null space and then figure out if that description that we have come up with is a basis or if it can be pared down further to a basis. So when we're finding the null space for a matrix A, let me just call this A. Keep in mind what we are trying to find are the vectors that solve AX equals 0. And the basic way that we do that is we do an augmented matrix and row reduce and solve. So augment A with a column of zeros and go ahead and reduce that and see what we get. Which is this. So we need to take that and find a description for the vectors that solve AX equals 0. So again, that first row, say x1, x2, x3, plus 2x4 plus 3x5 equals 0. I'm going to go ahead and move the other terms over to the other side. So x1, x2, x3, x4. So minus 2x4 minus 3x5, and the next one would be x2 equals x4 plus 2x5, and the last one would be x3 equals 2x5. We've got 2 free variables, so x4 equals x4 and x5 equals x5. And now I'm going to describe these in terms of vectors. So let's see, let me break this up and say this is -2, 1, 0, 1, 0 times x4 plus -3, 2, 2, 0, 1 times x5. Okay, this is something technically we could have done way back in chapter 1 if someone had just said solve this augmented matrix. You could have done that, and by chapter 2 you knew how to write the descriptions not just as equations but as vectors. And now we sort of know that we're actually looking at the span of a couple vectors. Furthermore, I can see that these two vectors are linearly independent of each other. They're not multiples of each other. So there's no extraneous bits here, and we have a basis for the null space. So the basis for the null space of matrix A is those two vectors. So if you're writing down a basis, you technically just write down the vectors. You don't write the x4 plus and x5. So you just say the basis for the null space of A is -2, 1, 0, 1, 0, and -3, 2, 2, 0, 1. And if you say that to someone else who understands linear algebra, they will know that, oh, I can take any multiple of the first one, add it to any multiple of the second one, so they'll kind of put it back in this form in their brain. And they'll say any 5-dimensional vector that I get by doing that will tell me how to combine these 5 columns to get 0. So we'll sort of have this description for everything that maps to 0 if we look at this matrix as a transformation or a mapping. Okay, let's do a couple more. 13 and 14, nicely enough, they did the row reduction for you already because doing the grunt work is not the focus at this point. So they said here's A, which has been row reduced to get to B. And they want you to find the basis for the null space and for the column space. Let's take the basis for the column space first of all. And let's just point out that the basis for the column space is the pivot position. So there's a pivot position there, there, and there. So a basis, and be careful here, the basis for the column space is not these reduced vectors. They just tell you where the pivot positions are. So the basis for the column space is going to be this one, and this one. That's those three together. Are the basis for the column space of A. On tests, pretty regularly, I always have a student or two that tells me that the B columns, first, third, and fifth columns of B are the basis. Which is not true. Again, just identifies the pivots. You can see that by combining the first and third and fifth columns of B, you'd never be able to get a non-zero in the fifth entry. However, looking at A, you can clearly see that the column space of A includes some things that have non-zeros in that fifth entry slot. So again, the columns of B are not going to do that for you. They help you pick out the columns of A that will. So they also want a basis for the null space of A. And again, we just did a null space example, so I probably won't walk through the whole thing again, but the basic idea is you still need to write out that so you would imagine there had been a augmented row of zeros there, but then you would start writing down things like x1 equals what? -2 x2, no x3s, minus 2 x4s, minus 5 x5s, and you do the same thing. The next one would just be x2 equals x2, but the next one would be 3x3 equals, and then you'd have to divide by 3, so you'd have x3 equals, well here, I'll do one more row. So that equals 6x4 minus 3x5, and again you'd want to solve for x3, so divide both sides by 3, so that would become x3, this would become 2, and this would become -1, excuse my messiness. And you keep going. x4 equals x4, and so you'd finish that out, you'd solve, you'd see it's a combination of x2s x4s, and x5s. And you'd be able to write out the null space. So I won't finish that one out. You'll get the idea there. And finally, for 15 through 18, which are some of the last problems on your homework, it says find a basis for the space spanned by these vectors. So again, now we're not talking about a column space or a null space directly. We're just talking about the span of these 5 vectors. It's 5 vectors in 4-dimensional space that guarantees that at least one of them is going to be linearly independent, maybe more of them. So I am not going to finish this one out for you, but you would dump this as a 4 by 5 matrix into a calculator, row reduce, pick out which ones are the pivot columns, and if the pivot columns end up just being number 1 and number 4, then you'd say those 2 are the basis and the other 3 are all extraneous. They're all linearly dependent from those 2, or whichever ones they end up being. Okay, I think with that you are ready to tackle the homework. And don't forget that fun true or false question that's coming at the end. That's always a nice way to finish off a homework, don't you think?